Hello and welcome to another episode of TWiML Talk, the podcast where I interview interesting people doing interesting things in machine learning and artificial intelligence. I'm your host, Sam Charrington. The show you're about to hear is the first of a series of shows recorded in New York City at the O'Reilly AI New York event. But before we get to the show, I've got a ton of updates and announcements for you. First off, I want to give a huge thank you to everyone who came out to our very first TWiML Happy Hour in New York City. There was a great mix of folks in attendance, including listeners from New York, O'Reilly AI attendees, and NYAI members. It was an awesome night. I want to especially thank Miriam and the rest of the team at the NYAI meetup for helping us pull this entire thing together, and for Clarify for supporting it. The O'Reilly AI conference itself was great, and of course, my favorite part was getting to meet so many listeners. I especially enjoyed meeting TWiML superfans Bill Berrien and Beth Ann Noble. They're both longtime listeners of the show and highly engaged members of this community, and it was just amazing to get a chance to hang out with them. I did a ton of interviews at the show, and I'm pleased to present them to you for your binge listening pleasure. We have got your commute covered for the entire week with this series. The series is brought to you by our friends at Intel Nervana. I talked about Intel's acquisition of Nervana Systems when it happened almost a year ago, and I was super excited to have an opportunity to sit down with Nervana co-founder Naveen Rao, who now leads Intel's newly formed AI products group. Naveen and I talked about how Intel plans to extend its leadership position in general purpose compute into the AI realm by delivering silicon designed specifically for AI, end-to-end solutions including the cloud, enterprise data center, and the edge, and tools that let customers quickly productize and scale AI-based solutions. I also spoke with Hanlin Tang, an algorithms engineer on that team, about two such tools announced at the conference: version 2.0 of Neon, Intel Nervana's deep learning framework, and Nervana Graph, a new project for expressing and running deep learning applications as framework and hardware-independent computational graphs. Nervana Graph in particular sounds like a very interesting project, not to mention a smart move for Intel, and I'd encourage folks to take a look at their GitHub repo at github.com/Nervana Systems, as well as their main site at intelnervana.com. One of the things announced at the conference is that Intel and O'Reilly will be partnering on the AI conference going forward, starting with the San Francisco event in September. They've also changed the name of the event to the AI Conference. To celebrate all this, we at TWiML are going to start our The AI Conference ticket giveaway early and run it through the end of the month. To enter, just let us know what you think about any of the podcasts in this series, or post your favorite quote from any of them on our series page, on Twitter, or via any of our social media channels. Make sure to mention at TWiML AI, at Intel AI, and at the AI Conf so that we know you want to enter. Full details can be found on the series page at twimlai.com/O'ReillyAINY. By the time this series drops, I'll have just returned to the States from my trip to Europe. I'll be back on the road later this month to check out the Wrangle conference in San Francisco on July 20th. You may remember that I recorded the very first TWiML Talk show with Claire Corthell at Wrangle, and Cloudera was my very first sponsor for the podcast, so I'm really looking forward to getting back there. I definitely hope to catch up with some TWiML listeners while I'm out there, so please check the event out. If you'd like to attend, I've arranged for a special discount for TWiML listeners using the code PCVIP. That's good for 20% off of registration. Finally, a couple of shows ago, I mentioned the idea of starting a paper reading group, and it turns out a bunch of you are interested, so let's make it happen. If you'd like to give some input on the details, visit twimlai.com/meetup and join the discussion in the comments. Actually, I've got one more finally. Longtime listeners will know that I've been talking about doing a newsletter since the dawn of time. Well, a friend and I were chatting the other day about how we've both been putting off launching our newsletters and ended up challenging each other to just do it. So look for it next week. And if you're not already signed up, please do so at twimlai.com/newsletter. Okay, apologies for the long intro, but now a bit more about this series. In addition to my conversations with Naveen and Hanlin, this series is packed with more interviews that I know you'll love, including my conversation with Doug Eck of Google Brain's Project Magenta, in which we discuss the intersection of AI and art in general, as well as Google's recently announced Performance RNN project, which was demonstrated for the first time at the O'Reilly AI conference. Ben Vigoda of Gamelon, in which we discuss probabilistic programming. This one I think is nerd alert worthy. Reza Zadeh of Matroid, about how his company is scaling video object detection. And Rana El-Kayoubi of Affectiva, about how her company uses emotional AI to allow brands to better measure the effectiveness of customer experiences. All right, enough meta. Let's jump right into the first episode of our O'Reilly AI New York series. After the bumper, you'll hear my brief interview with Naveen, and immediately after that, my interview with Hanlin. Enjoy. So hey everyone, I am here with Naveen Rao. Naveen is the Vice President of Intel AI Product Group, and we're here on location at the O'Reilly AI Conference where he just delivered a keynote. Naveen, how are you?
Great. I think it went over pretty well, short and sweet. Got to announce a few important things around some of the open source projects we have going on, as well as our direction of end-to-end AI.
Great. Why don't you tell us a little bit about the announcements you made?
Yeah, so one of them was about Intel Nervana Graph. This is almost an abstraction layer for hardware, basically collapsing primitives from different deep learning frameworks into a common representation that we can then optimize for different types of hardware platforms, CPUs, GPUs, our new architecture, FPGAs, that kind of thing. So it really lessens the burden on optimizing each framework for every new hardware platform out there. I think this is something we want to drive forward as a standard in industry. And the other one is we released Neon 2.0, which is our reference standard framework for deep learning. And this supports Intel architectures, CPUs. The latest CPU that's going to be launched from Intel will be supported by this framework and optimized highly.
Okay, great. And I've got a conversation scheduled with one of the technical folks at Intel, Hanlin, for later on. So we'll dig into some of that, but I wanted to also just kind of get a pulse from you on, it's been almost exactly a year since the acquisition.
It's been about 10 months now.
About 10 months?
Yep.
How's it going, and what have you been up to? What's been consuming your time besides from the announcements that you just made?
Yeah, it's been a ride, actually. So when we came in to Intel, we were a 50-person startup. Now we've formed an entire new division devoted to AI, kind of seeded from that 50-person startup, and it's much bigger than that now. Mm-hmm. So it's actually been quite exciting to bring together the resources that we have at Intel and actually drive a bigger picture, a broader portfolio of products and solutions to the industry. The way we think has to change a bit. As a startup, you're trying to be scrappy, you're trying to get that next deal. Now we can think in a much bigger way, right? We can say, well, what can we do that'll have a maximum impact across the entire industry? Mm-hmm. The sales channels and relationships that Intel has with enterprise is just enormous. Mm-hmm. 6,000 salespeople can be unleashed, right. Which is just a different way of thinking entirely from a startup.
Absolutely, absolutely. If I can kind of dig right in, one of the, what I think of like the elephant in the room when I think about Intel is, at the chip level, NVIDIA was kind of at the right place at the right time for AI with their GPUs. And a lot of people think that they've got a big head start in the market. And, I wonder how does Intel think about that, and what's the plan?
I mean, there's no doubt they're executing extremely well. They're doing a great job. They've adapted their architecture for these kinds of problems pretty well. Head start, sure. Yahoo had head start over Google too. So there's a lot of examples to the contrary there, and I welcome the competition. I think we're at a point now where obviously there's never going to be one provider for these things. Intel really owns the host processor in the data center, the heart mm-hmm. of it. The huge software investments that have been made in terms of building the internet, right? Things where you can really scale out infrastructure, make it reliable. Like when you hit a website, it works every time because of all the software investment built on top of Intel architecture. So we're leveraging that, mm-hmm. and actually most AI solutions that are deployed in the data center are actually running on Intel.
Right.
So we have those things. We're enabling them with our software stack today. Some of the announcements I made are relevant to that. We're adapting our main product lines for these purposes, and we're also going straight for AI as a preferred workload, essentially for acceleration. So you'll be seeing some announcements in the next 6 months to a year around our silicon in that space as well.
Okay. You guys have made some pre-announcements in terms of the broad brush roadmap. Can you walk us through what we should expect to see?
Sure. So that was really based on the roadmap we had from Nervana as a small company. So we are developing the silicon that we were developing at Nervana. It's going to be in prototypes this year, and we're really taking the learnings from that. Building a real new architecture for this kind of workload is not simple, right? It takes a few iterations. So we're not really announcing products beyond that in terms of roadmap, but we are basically going to have products out in 2018, 19, 20. We have an entire roadmap there. We're not talking about performance just yet. But, I mean, we do have some really important and exciting things on the horizon from the silicon engineering side as well. So AI is a great showcase for those capabilities because density of compute and power per operation matter a lot.
Right.
So that's something that it's right in Intel's wheelhouse.
And then speaking of density, a big part of the Nervana story was around cloud. How are you guys thinking about the role of cloud with regards to AI?
So yeah, that's a really interesting question. So part of it is actually we're continuing our hosted cloud service. So we're calling it Intel Nervana Cloud. We look at that as very, very much a quick way of getting going on a solution for an enterprise. In addition to that, we want to bring those capabilities on-prem for our enterprise customers who don't necessarily want to move data off their premises. And so that's kind of the products you'll be seeing in the next year or so. Then obviously broader industry, cloud service providers are a huge customer of Intel. So Amazon, Google, Microsoft, the big ones. So they're all developing their AI platforms and we're supporting that effort. It's basically a different kind of customer for us, but we look at it as basically they intercept at different points in the stack.
Right.
And so I think you're going to see a variety of solutions ranging from fully in the cloud to hybrid on-prem cloud and completely on-prem.
Okay. Oh, great. One of the announcements you made was around the Nervana software stack. Can you talk about how that relates to some of the other frameworks that are out in the marketplace? TensorFlow, for example, has gained a lot of traction. I think my impression was that Nervana's stack was initially positioned as an alternative to something like a TensorFlow. Is that still the case? And how do you see the landscape there?
Yeah, so when we first started Nervana, actually there was no TensorFlow, right? There were a few fragmented frameworks. We put Neon out at that time, and it is still an alternative to TensorFlow. It kind of works at the same semantic level.
Okay.
We are keeping that development going as a reference standard. People can obviously build on it, and we're supporting it. That's good for us because it allows us to bring the latest optimizations that we have for hardware to the open source community quickly. We're not beholden to anyone else who owns the database, basically.
Right.
So we can get those out. Intel Nervana Graph is about supporting everybody else's frameworks. So if you go to intelnervana.com, you can actually see how we're plugging TensorFlow into Intel Nervana Graph and allowing it to be optimized on various hardware platforms. So we want to play in the community that way, but we can control the ecosystem from the Neon side and provide the latest innovations there. And it'll take a little bit longer for it to trickle down into the rest of the open source community.
Okay. What are some of the specific ways today that the hardware innovations are surfacing into the Neon framework?
I mean, some of these things we can't talk about just yet, but the way we're going to do parallelism and distribution of workloads. We have some novel constructs and the way we handle memory and things like that.
Okay.
It's not to say we couldn't make it work in other frameworks, but we'd have to really fork it and do things a little bit differently. So we can get those new concepts out. And I think now what's cool about being part of such a big company is that we can actually shape how the rest of industry sees this. So we get those things out. I think researchers start playing with it, and we'll start seeing changes happening in all the frameworks probably.
Okay. I'm sure it'll be interesting. I've seen a similar path happen with the Intel investment in Cloudera and how they push a lot of the security and encryption innovation and other things like that into the Hadoop ecosystem.
That's right. Yeah,
it'll be interesting to watch.
Yeah.
So I think we're about at our time. Anything else you'd like to mention to the listeners?
Well, I think the partnership with O'Reilly is very exciting for us. I think we're at a time in industry where we're seeing adoption happen quickly, and so O'Reilly has been, on the Strata Hadoop side, has been really a big player in that. And so I see a parallel happening with AI as well. And so I hope to see this this grow for O'Reilly, and we'll be part of it. So.
And you just announced a strategic partnership where you guys are the exclusive partner for the O'Reilly AI conference going forward?
Not exclusive. We'll still take on other partnerships, of course, with them, but we are the main headline sponsor, yes.
Okay. Analogous to the Cloudera and
exactly.
Strata Data now
you got it,
conference. Yeah. Okay. Awesome. Well, looking forward to seeing you in September at O'Reilly AI San Francisco.
I'm looking forward to it as well.
Awesome. Thanks, Naveen.
All right. Thank you.
Hey everyone, I am here with Hanlin Tang. Hanlin is a senior algorithms engineer with Intel Nervana. Hanlin gave a talk here yesterday at the O'Reilly AI conference, and we're here to talk about his talk and what he's been up to. How are you doing, Hanlin?
Good. How are you?
I'm doing great. Why don't we start by actually having you talk a little bit about your background and how you got into AI and algorithms?
Yeah, of course. I guess it mainly started when I was in graduate school. I was doing research in computational neuroscience, and that's really where the connection between understanding how the brain works and attempting to transfer some of that knowledge into silicon and computer systems really took hold. And so after graduate school, I joined Nervana, which is a deep learning startup, and through that I've begun to sort of apply the research that I did in graduate school to some of the applications that Nervana is developing. Then now, of course, as Intel, we have the opportunity to scale that out quite significantly across all fronts, hardware, software, algorithms.
Great. And you gave a talk here yesterday at the conference?
That's right. I think I mainly focused on how do we do that exact same process that I had just described of taking research, these sort of algorithms and models that you see in the scientific literature, and then begin to apply them and deploy them into production settings.
Okay.
There are sort of unique challenges that you face when trying to do something like that.
Why don't we have you walk us through that? I know myself and a lot of our listeners will read papers and walk through, the latest cutting edge research and try to understand how to implement it, but putting it into production is a whole nother issue. So how did you frame that up in your talk?
I think I mainly focused around three key aspects. So the first one being the lack of data. So I think we've often heard that there's a flood of data in the world today. And certainly with Fortune 500 companies and government agencies, there's a large corpus of data. But all that data has to be funneled through a very small pipe of manual annotations, because to existing methods, we need a human to actually go through and put boxes around all of the cars for thousands of images before a model can learn to do it.
So we're data rich but labeled data poor.
That's right, and being able to navigate that environment with either heavy investments in data or some of the newer techniques in generating synthetic data from what you already have is sort of quite critical in building applications that perform well. Because deep learning particularly requires a large amount of data to reach the level of performance that sort of exceeds what humans can do.
So on your first point then, with regards to data, there's clearly, there are ways to take this on manually by, just investing in labeling data. But on the synthetic data side, what's happening in that part of what kind of activity is happening there?
So one great example is from Intel Labs, where they have used video games to generate some realistic imagery by sort of getting graphics artists and such to build out a video game environment, to use that sort of build the synthetic data in order to train many of the autonomous driving applications.
Okay.
Or alternatively, there have also been advances in using generative adversarial networks to also generate realistic imagery that could be used during the training process.
Oh, interesting. I think I've seen examples of using video game data to train autonomous driving programs. At the time, I thought the results that I saw suggested that for whatever reason, the results didn't transfer very well. Did you guys in the lab research that you're referring to find some ways to address that?
I think that's still an active area of research, is how to generalize. But they did find that if you're able to augment your existing real-world data set with the synthetic data set, you do get better performance overall. Because this transferability problem exists for real data sets as well, where you may collect large amounts of data in one city, but not able to generalize to other cities or other environments.
Okay. Oh, interesting. Yeah.
The other sort of aspect that I highlighted was building a feedback loop into your systems to have annotation occur on the edge. And what I mean by that is if you're building, say, an aviation security application, when you have sort of detectors at the scanning sites looking for dangerous objects and baggage, you also want to build in a system for the agents to provide feedback on how the algorithm is doing. And in that way, you build a sort of cycle of collecting data and monitoring data in production.
Right.
And we've seen that to be quite critical because the world can change underneath you. So objects that may be more popular during the summer may be less popular in the winter. So being able to monitor those changes of the distribution of objects that you expect to see and modify the algorithm appropriately is quite critical.
That's an interesting point. I know a lot of startups are, founded basically around this idea of collecting data and allowing consumers to basically annotate models for them, annotate data for them. But I can imagine enterprises building these systems and putting them out and not kind of closing the loop.
That's right. It's relatively easy to close the loop when it's just a web interface where the closing the loop is quite simple. But in autonomous driving or aviation security or many of these other applications where physically the inference occurs on the edge, you actually have to build in the networking and the storage and the memory and also the sort of components that Intel has in order to close that loop in many of these scenarios.
Okay. All right, so you talked about data as one of the first elements of being able to put these systems into production. What else did you talk about?
The other point that I really wanted to highlight was around model selection. It's a difficult challenge these days because for any particular task, such as object localization, you will find many models in the literature. So faster RCNN, single-shot detection models, RFCN, and there are always newer ones coming out all the time. So Intel recently has PVA-Net as well. And how do you make a decision as a data scientist of what models to choose? And I guess what we've seen is that many customers may sort of just choose the latest model and run with that, where sometimes you have to make very fine-grained speed, accuracy trade-offs around your particular use case. So a particular model may be more performant, but also take longer to train, in which case your iteration cycle is slower.
Right.
Or
and your training costs are higher.
Yes, and your training costs are higher. Or some models may perform better than another model on sort of an aggregate performance metric, but perhaps one model will perform better at small objects compared to large objects. And so being able to make that fine-grained determination, not just on sort of an average metric level, but also splitting it up into the individual categories depending on what you're interested in, is what we found to be valuable for many of our enterprise customers.
Do you find that understanding the various trade-offs, to what degree is it dependent on a very specific use case and a specific data set? And I guess the broader question is it possible to kind of come up with some standard metrics around, in a given category like object detection or speech recognition and, rate the different algorithms according to, some set of standard metrics? I haven't seen anything like that, but it would certainly be helpful to folks that are, coming into a space like object detection and trying to figure out where to get started.
There are certainly ways to do that. So there was a recent paper by many of our colleagues at Google on doing exactly that, measuring the various types of object detection models on performance and speed. And that is sort of valuable work to help guide many of our customers. And that determination is somewhat general across different use cases within object detection. However, for your particular use case, you need to dive much deeper than that. It's not enough just to look at the overall mean average precision, which is the metric that they use. You then have to split it out by particular pedestrians or motion, large objects, small objects, and that determination is much more use case specific.
And then in this paper that you're referring to, did they also consider practicalities like training time and training costs, things like that?
They did not. I think they were mostly focused on the inference side of the equation. So that's certainly valuable work moving forward.
Interesting. So what else did you cover in your talk?
I think those were the three sort of main points I made around data, closing the loop, and model selection.
Okay.
I guess if I were to add a fourth one that I had mentioned was knowing your model provenance. So going back to the object detection example there, that model and many of those models are designed for specific data sets. As a grad student, you build a model around specific benchmark data sets to help guide you on how you are doing. And so in particular, two data sets, Pascal VOC and MS COCO, have been very popular for object detection. But those data sets typically have maybe 5 to 10 objects per image. If you're trying to transfer that same object detection model to do a different application, such as satellite imagery, suddenly you have a scenario where the data set statistics don't match the benchmark data set that the model was designed for. Right? In satellite imagery, you have hundreds of objects in a particular image. You have rotational symmetry because an aerial image can be rotated and retain many of the similar properties. You have boxes around buildings that are no longer, that are rotated. And so now you need to additionally predict an angle in addition to the coordinates. And so we've been actively developing ways to adapt existing models to that application. So even though both tasks are object detection, knowing where the model came from and what it was designed for can help you sort of maximize the performance on your particular application where the statistics may be completely different.
Yeah, this comes up all the time in the context of the research community and the practitioner community kind of, quote unquote, overfitting on ImageNet, right? And it sounds like some similar things are happening in the object detection realm where there are some standard data sets that, folks are building models on and then trying to apply all over the place. Knowing the provenance of your models is one thing. It sounds like you're also then coming up with techniques that allow you to generalize and adapt those models to new situations. In the case of satellite imagery, for example, how exactly what's kind of the underlying techniques that you're using to enable the model to adapt to a different use case?
It's really doing surgery on the model itself. So in this particular case, existing object detection models in the literature mostly just predict the XY coordinate of the upper left corner and then the width and the height of a box. And so we are working on modifying that to additionally predict rotation angle, for example, or dealing with multispectral satellite data where it's not just red, green, blue in the image, but IR, near IR as well. So there are also these other spectrums that we can begin to build a model to take advantage of.
Okay, so we're talking about evolving the models themselves as opposed to we're not training a model on the original data set and then using some techniques with a trained model to give it better inference in a new scenario. It's, we're talking about how do we build a new model that is better adapted to this situation.
Yes, exactly. I mean, don't get me wrong, these existing object localization models are very powerful.
Oh, absolutely.
5 years ago, as a grad student, I would never have imagined a world where these sort of applications can be done and not only be performed well, but at real-time speed. It's quite incredible. And so we're really sort of standing on the shoulders of sort of these papers, but then iterating further for particular use cases where you need to make some changes.
Okay. And then I think in your presentation you also talked a little bit about the Nervana stack and what was happening in that area.
It's an exciting time for us. We've spent the last 2.5 years building a full stack for deep learning, and I think as Nervana and now as Intel, we still firmly believe in that philosophy that you need the full stack in order to get maximal performance and ease of use out of what we're building. So it's everything from the custom silicon to our software work up to a cloud or platform service, and then finally to applications. And now that we're part of Intel, we have an opportunity to supercharge those efforts in a sense. And so as Naveen had mentioned, we've released Neon 2.0, which Neon previously was known, when we were a startup, as one of the fastest frameworks on GPUs due to the custom assembly kernels that we wrote and some of the algorithmic innovations that we introduced with Winograd convolution. And now we've been working very hard with other engineers at Intel to also optimize Neon for Intel architecture. And so by integrating into Intel's math kernel library, we can achieve quite significant speed ups. So on an image classification model such as GoogleNet, inference is about 98 times faster than previously. So these are very serious optimizations that Intel has done for other frameworks as well, such as TensorFlow and MXNet. And we're excited to work with them to now bring many of these optimizations into Neon as well.
Okay. For those that aren't familiar with Neon, can you walk us through the design philosophy and how it differs from some of the other frameworks that are out in the market?
Of course. So Neon, we really designed for enterprise use cases where speed was quite important. And many of our customers don't really need the model of the week. They want a stable and fast and optimized object localization model or speech recognition model. And that's really what we provide to many of our customers. In addition, we pay a lot of attention to data loading because the folks that we talk to at O'Reilly, those that run companies that build applications, they don't train their models on ImageNet or on MS Coco or on PenTreeBank. They train on their own custom data sets.
Right.
And so we put a lot of effort into designing modular data loaders that are fast but also flexible. And easily provide a data API for users to switch between different models. So if I'm doing an object detection model, we have a couple that we've implemented. There's a common data API for loading that kind of data so that you can test different models relatively easily.
Okay. Are there particular use cases beyond the ones that you've mentioned that you've found to be the sweet spot for Neon relative to other frameworks?
I think we found use cases across a variety of domains. So not just in image that I mostly focused on, but also in speech recognition, where we've developed a model based on Baidu's state-of-the-art Deep Speech 2 model. In natural language processing, which many of our financial customers are using. I think one of our sort of MOs is to keep track of the quickly changing literature for new models coming out that bring new level of capabilities, and then porting them into Neon and then optimizing them for speed and for stability and for ease of data loading. And that's really where we find the value to provide to many of the folks that we work with.
One of the challenges for enterprises putting these types of machine learning models into production is monitoring their performance over time and then building a feedback loop that allows them to improve and enhance their models. Does Neon have anything in particular to offer in that scenario?
Yes. So in Neon, we've built in callbacks that allow the model to report back its progress, either during the training process, but also actually mostly during the training process. We don't have anything currently for sort of specially built for monitoring and inference. But that's certainly a good idea that we can look into.
So in addition to the Neon 2.0 announcement, you also announced the Nervana Graph product. Can you talk to us a little bit about that?
The Nervana Graph project really started even before we were acquired at Nervana, when we realized that many of the newer models coming out, attention-based models, for example, were much easier expressed in a computational graph. And that's really the core of the effort that we're doing, where we've really rethought the back end of Neon. And with the Nervana Graph effort, we built and we're in the process of designing a a Nervana Graph intermediary representation, which different frameworks can then hook into.
Okay.
And then on the back end, different hardware backends will take the graph emitted from Nervana Graph and then apply their hardware-specific optimization passes to eventually build an executable execution graph that can run on different devices. So at Intel, we're fortunate to have a variety of hardware targets: Xeon, Xeon Phi, Future Lake Crest, Movidius, FPGAs, and having a common tool chain to allow folks to train on one hardware device and deploy on another one, or train on a heterogeneous mixture of hardware devices, we think will really change how models are being developed and make it much easier for industry to transfer those models, between these different devices.
Can you talk a little bit more about graph as a paradigm for building out these models? You mentioned attention-based models as an example. What's the relationship between, a graph-based view of the world and attention models, and how does a graph framework support building that kind of model better?
Fundamentally, neural networks are graphs of computations. And representing that directly in the Nervana Graph framework and allowing folks to interact with the graph in building these models will allow much more flexibility than what we had originally envisioned with Neon.
Okay. And so is the idea that for an arbitrary network, my different layers represent nodes in the graph, or what does a node in the graph represent?
So a node in a graph represents a fundamental operation.
Okay.
Like adding or exponential function or matrix multiply.
Okay.
And so layers, which is a higher level concept, each layer implements a graph of operations.
Okay.
And when we string together layers, we're essentially adding components and nodes to the graph itself. And that's during the construction phase. And after that construction is complete, we now have a complete view of the exact operations that you need to do to train your model. And from that, we can then apply optimization passes to reduce unnecessary computations, to optimize memory usage, and also take into account the specific data layout requirements of different hardware.
So how does the developer experience change in using the graph project? Would you call it a project or a product?
I would call it a project.
Okay.
But I'm an engineer, not a not a products person, so I'm not quite sure what the exact semantics are.
Yeah. So it's clear that, thinking about a neural network as a computational graph and kind of having that explicitly laid out allows us to, perform optimizations, just like, a compiler might, or like a query planner in a database might. Is this something that's happening at the developer level, or is it kind of shimmed in underneath an experience that the developer might already be using, like Neon or TensorFlow or something else?
If you're a developer that principally uses components that have already been written out, so layers like convolution and pooling, then your experience will be relatively similar. If you have to develop new layers or apply some custom computation, then you're able to access this node level directly and develop on that. So you can compose the ops yourself into a graph. And in many cases, we find that the latter brings a lot of value because not everyone is just sort of applying the sort of vanilla models and layers that have already come out there.
In part for the reasons that we previously talked about. They don't apply as well to, some problem sets or data sets than a model that's been, augmented to meet the specific needs of that data set.
Right. And in many cases, it's not just the different layers that they're composing together, but also the way they're composing them together. So I have a bunch of layers coming in, and I want to fork that into outputs that get broadcast to multiple streams. Or I may have multiple streams of data coming in, whether it be images and video and text. I want to be able to concatenate that together. So the graph also allows that to be much easier than before. Because if we know the graph, we know how to do the forward and the backward passes during the training regime. Whereas before in Neon, you would have to explicitly guide the model towards, okay, I have this topology, do the forward pass this way, and then pass the outputs across this fork, and then collect the gradients, etc. So the graph takes care of a lot of that. So it's much more composable, is one of the key points.
Okay. Oh, super interesting. How can folks learn more about the Neon and the Graph projects?
I definitely encourage listeners to check out our GitHub page, Nervana Systems. There is a repository for Neon and also for NGraph, which is the Nervana Graph. Additionally, if you go to www.intelnervana.com, we have a couple blog posts that introduce sort of the framework itself, how to use it, links to the model zoo, where we have a lot of pre-trained models that folks can easily get started with. And we definitely encourage the community to contribute as well. The Nervana Graph effort is still in the early stages. We are sort of releasing our sort of latest commits quite often. But definitely if users look into that and see a feature that they like, that they're missing, we definitely welcome external contributions.
Awesome. Anything else you'd like to mention?
I think that's it. I'm excited to be here at O'Reilly talking to you, and happy to continue the conversation in future meetings.
Fantastic. Thank you, Hanlin.
Thank you.
All right, everyone. That is our show. Thanks so much for listening and for your continued support, comments, and feedback. A special thanks goes out to our series sponsor, Intel Nervana. If you didn't catch the first show in this series, definitely check it out. If you didn't catch the first show in this series, where I talked to Naveen Rao, the head of Intel's AI product group, about how they plan to leverage their leading position and proven history in silicon innovation to transform the world of AI, you're going to want to check that out next. For more information about Intel Nervana's AI platform, visit intelnervana.com. Remember that with this series, we've kicked off our giveaway for tickets to the AI conference. To enter, just let us know what you think about any of the podcasts in this series, or post your favorite quote from any of them on the show notes page, on Twitter, or via any of our social media channels. Make sure to mention at TWiML AI, at Intel AI, and at the AI Conf, so that we know you want to enter the contest. Full details can be found on the series page, and of course, all entrants get one of our slick TWiML laptop stickers. Speaking of the series page, you can find links to all of the individual show notes pages by visiting twimlai.com/O'ReillyAINY. Thanks so much for listening, and catch you next time.